Evaluate the triple integral using cylindrical coordinates. And we're integrating over E, which is the solid domain region, under the paraboloid z is equal to 1 minus x squared minus y squared. The first thing that we want to do is to graph this domain region. And in order to do that, I'm going to try to get it into more of a standard form to make it a little bit easier to recognize it as a paraboloid. So this paraboloid is going to have a vertex point at 0, 0, 1, and it's going to be opening down, creating circular trace curves when it's sliced with constant z-planes. But since we're only interested in the solid that occurs in the first octant, we erase a good portion of that and focus our attention up here. Now it's time to create the triple integral. And we'll also go ahead and convert everything into cylindrical coordinates, which means that for every x value we'll plug in our cos theta, for every y value we'll plug in our sine theta, and any z value, if we had them, would remain as a z. And so for this first term, x cubed is going to become r cos theta quantity cubed plus another x value, which is r cos theta, times y squared, so that's r sine theta quantity squared. And now we need to decide what we're going to do with dv. Remember, dv is going to contain a factor of r, and then we get to decide, do we want to integrate with respect to r, with respect to z, or with respect to theta first? So here's where we go into the domain region, and we graph a little tiny polar rectangle. And we think about floating it in the direction of r. And throughout this domain region, we would have the same lower limit, which is r is equal to 0, and the same upper limit, which is that paraboloid, no matter where we are in that domain region. We could also float with respect to z first. The lower limit on z is equal to 0, and the upper limit on z is equal to the paraboloid, no matter where we are in that domain region. And in this case, we could also float in the direction of theta first, which would be kind of wrapping it around. Our lower limit on theta is going to be 0, and the upper limit on theta would be pi over 2, no matter where we are in that domain region. We're going to hit the xz wall on the low side and the yz wall on the high side. So we can really do whatever we want, and I actually think I'm going to choose to go r dz dr d theta, integrating with respect to z first. And the reason I choose z first is because in the second iteration we're going to have to project into the floor of the remaining two variables, and I just find it easier to project into that xy plane where I can clearly see r and theta. So in for our dv, we'll substitute r dz dr d theta. Now, let's also mention that this factor of r should be multiplied by the entire quantity here. So let's go ahead and wrap that up just to be sure we don't forget about that. And now let's go ahead and think about our limits of integration. With respect to z, remember the floor is our lower limit, so z is equal to 0. And the paraboloid was our upper limit, so we need to make that substitution that r squared is equal to x squared plus y squared, which makes our z equation now 1 minus r squared, and that's going to be the upper limit for our inside iteration. And now let's project into the floor, and let's be reminded that this as x and y values, we have 1, 0, 0 here and 0, 1, 0 over here. So in the xy plane, we basically have this quarter circle. And when we think about that polar rectangle, and we've already said that we want to integrate with respect to r next, so the lower limit on r is going to be 0, and since this is a circle, the upper limit on r is going to be the radius of positive 1. So r is going to go from 0 to 1, and then when we sweep this band all the way to the bottom, that tells us that we have a lower limit on theta that's 0, and then when we sweep it all the way up to the top, again we have a theta value of pi over 2, so those are the limits on our theta iteration. And now we're ready to integrate. Let's go ahead and distribute in this r, and as well cube this quantity and multiply all this together. And since we're integrating with respect to z, all of this is one big constant. And so the antiderivative is going to be that constant times z, and then we apply our z limits from 0 to 1 minus r squared. And these get plugged in for just the z values. So let's take this constant and pull it to the outside of our antiderivative with the upper limit plugged in for z minus the lower limit plugged in for z, which of course is just 0. And now we're looking at this multiplied by all of this. Let's pull out the r to the fourth and one of the cosines. And what we have left from the first term is just cosine squared, and what we have left from the second term is sine squared. And then all of this is equal to 1, and we still have 1 minus r squared that we'll need to distribute in. So this becomes r to the 4th cos theta minus r to the 6th cos theta, which is now the integrand for our second iteration. And now we're integrating with respect to r, and the limits of integration are from 0 to 1. So our first term is cosine times r to the 5th over 5 minus cosine times r to the 7th over 7. The limits are from 0 to 1. Let's factor out that common cosine. And when we plug in the upper limit of 1, we'll get 1/5 minus 1/7. And when we plug in the lower limit of 0, everything zeroes out. And so we get cosine times 2 over 35. And that becomes the integrand of our third iteration. And now we're integrating with respect to theta, and our limits of integration are from 0 to pi over 2. The antiderivative of cosine is sine, and then we apply those limits. First, we plug in the upper limit of pi over 2 into the antiderivative, and then 0. Sine of pi over 2 is 1, sine of 0 is 0, and so our final answer is just 2 over 35.